And I think we are ready to move forward to our next presentation. Project C123, we have Alejandro Romero Limones, a joint PhD student in the Laboratory of Chemical Technology from Gent University and in Laboratory of Catalytic Reactor Engineering, applied to chemical and biological systems from the Metropolitan Autonomous University in Iztapalapa, Mexico. During his PhD, he has been working with the C123 project on the characterization of fluid dynamics and heat transfer mechanism. He will be presenting further his presentation, Catalysts and Processes for the Conversion of Methane to Carbon Monoxide and Ethene. Thank you. I'm passing the voice.
So I would like to start this presentation with the motivation behind this research, which is the methane valorization. So, well, we know that methane is the compound with a higher portion in a gas mixture on natural gas and biogas. So worldwide, there are a large amount of natural gas reserves and also small opportunities on biogas that are waiting to be valorized into well, high-value products. By developing new processes for the methane valorization, we can impact in the environment and also in the economics. Environmentally speaking, we know that methane is a potent greenhouse gas, and reducing its emissions can collaborate to reduce also the impact that it has on these environment issues. Also, nowadays, the methane conversion is done on high energy intensive processes, as could be the steam reforming. So we're also trying to look into new processes that can be less energy intensive. In terms of the economics, natural gas is flared. So basically it's wasted in the atmosphere because in the petrochemical industry, they release this gas in order to release the pressure from the wells. So we're also looking the valorization of gas into products that can be compete in the market. So what has been done on the methane valorization? Well, the oxidative coupling of methane, the OCM, is the most the most promising option to convert methane into C2 species. Nowadays, almost all the periodic table has been researched in order to obtain the most suitable catalysts and operating conditions to reach the maximum yields possible to satisfy the industry needs on these products, mainly ethylene. Some European projects, as Memrea, Dremor, Ockman, has been focused trying to obtain these catalysts and also the operating conditions, aiming high yields of ethylene. However, they have concluded that from the moment there is no combination of catalysts and operating conditions that can reach these higher yields, and also because they're being focused on the C2 species, another issue have is that to separate ethylene and ethane, it is needed high energy intensive processes. So with that, the C123 project arose, trying to focus also in the exploitation of the same reactions as the production of CO and ethylene for the further hydroformylation of ethylene. So with this, one of the questions that the project tries to answer is, what if cheap methane sources could be bring high C3 products while largely reducing their carbon footprint? So the outline of the presentation, first, a small overview of the C123 project, then I'll present the catalyst candidates for the oxidative conversion of methane, then the developing of the kinetic model based on experimental results, the performance of the outcome process, and finally the conclusions on the future work. So the C123 project aims the valorization of methane from widely available unexploited resources, passing from methane through the OCOM reactor DOCOM process, obtaining an optimal mixture of CO and ethylene, then later formulation of ethylene to produce C3 species. So in the work package 2 of this project, we are focused on the oxidative conversion of methane. So for the OCOM, the oxidative conversion of methane, that shouldn't be confused with the OCM, which is the oxidative coupling of methane. To this moment, this is a black box, and we are trying to obtain the maximum yield of C2 of ethylene, but with a equimolar mixture of CO. So first, some OCM catalyst candidates were tested based on literature research. So the catalyst candidates were the lanthanum strontium supported on calcium oxide, manganese-based catalyst supported on silica and alumina. And I would say that the last material is not a catalyst, but it's an inert material that can support high temperatures up to 1,000 degrees in order to see what could be homogeneous reactions on the fixed bed reactors. So once we identified the most suitable catalyst, more experiments were done in order to determine the optimal operating conditions. And then with the experimental measurements, this experimental data, we developed the kinetic model for the OCM, and also because the high exothermicity that can be reached in the OCM, the energy is taking advantage to use the thermal dehydrogenation of ethene in the postbed cracking. And finally, with the kinetic model of both reactions, the simulations for the oxidative conversion of methane process is done on their real scenarios evaluations. It could be natural gas or biogas. Now for the catalytic performance test, well, first, the lanthanum strontium catalyst was tested. Here, before presenting all these results, I would like to say that the selectivities and carbon, the conversions are based on carbon-based. That means that because we have multiple carbon species, selectivities were calculated in this way. So for this material, we found that there is an excess of CO2, which is not the most suitable catalyst, at least for the oxidative conversion of methane. Also, the manganese-based material supported on alumina was tested by the University of Gent, provided by one of their partners, the catalyst. And we also find that there is an excess of CO2, which is not suitable for the OCOM needs. So then the same catalyst, but now supported on silica, show a nice performance regarding the selectivity to ethylene, and also at relative high conversions, which is 30% of methane. More tests were done with our partners from Total Energy in a pilot plant's packet bed for the alumina at harsher conditions. That would be temperatures 950 and 1,000 degrees, showing that even homogeneous reactions at those conditions has a selectivity up to 30% for the ethylene, high conversions of methane, but also the production here for the CO2 is high. So we are trying to focus in this catalyst, but of course, homogeneous reactions can also have this kind of performance. So with the experimental data obtained here, now more tests were done, trying to elucidate what could be the impact of the operating variables, and also developing the kinetic model. So here I'm presenting the impact of the methane to oxygen ratio at lab scale conditions. Here, well, what I also would try to remark is that this purple line is the sum of the two CO2 species, which is ethylene and ethane, and the rest of the species are, well, referred here with the proper colors. So based on this screening test, we could see that the primary reaction, well, the primary compound is ethane. So we can assume that the oxidative coupling of methane is happening. This is the methane is oxidized to produce ethane, and this reaction is increased as the ratio between methane and oxygen is increasing. That means more methane than oxygen. Also, we can see that if there is more oxygen in the feedstock mixture, the selectivity to ethylene is increasing and the selectivity to ethane is decreasing. This means that the ethane can be oxidized to produce ethylene. Another thing so in the experiment measurements was that also as the oxygen is increasing in this feedstock mixture, we have more CO than CO2. So at least for this catalyst, the partial oxidations are more likely to happen than the total oxidations of methane, or in this case also ethylene. But also because we have CO2, well, the production of CO2, some total oxidation should be considered in the kinetic model. So in this case, we propose the methane, the total oxidation of methane, because the conversion of methane is also increasing as more oxygen is in the feedstock mixture. So with this, with these results, we can propose 5 oxidation reactions for the kinetic model. Now, the impact of the temperature. Well, here we see that the selectivity of the CO2 species, it keeps the same amount as the temperature is increasing from 800 to 150, but the selectivity to ethylene is increasing as the selectivity to ethane is decreasing. So ethylene is produced from ethane, from the oxidative dehydrogenation of ethane, but also could be because the thermal dehydrogenation of ethane when oxygen is completely consumed. So that's why we also consider this reaction on the kinetic model. Then the impact of the CO2, because this model will be tested under real scenarios in which CO2 is part of the feedstock. So one thing we can see here first is that the CO2 has no significant effect on the methane conversion, but decreases the selectivity towards the other compounds. So here, this is probably because the way in which the selectivity is calculated. So it's not because there is more formation of CO2. Well, yeah, there is more, but it's also because the formation of the other products are reduced in compared with the CO2 production. But because all the reactions, or the oxidation reactions proposed here produce water, it is not so, it could be a nice assumption that the water gas shift reforming reaction is happening, and that's something that could also increase the selectivity to CO2. So based on this experimental resource, these 7 reactions were proposed. So the thing is that following regression and estimating the parameters for the kinetic model, we had the trend of the selectivities seen in experimentally, but we haven't reached the methane conversion. So following the same assumption that we have enough water on the reactions and the water gas shift reaction is happening, we also propose the steam reforming of methane in order to achieve the methane conversion seen experimentally. So with that, the regression shows a nice fit between the selectivity and the methane conversion calculated and those seen experimentally. So with this, the kinetic model of 8 steps is developed and proposed. And here I'm showing the parity plot. So as you can see, it has a nice fit between the calculated molar flow and the observed molar flow. Of course, the parameters here show us statistical significance, and they are on the same magnitude order as those reported in literature. So with this kinetic model, the outcome process is simulated. But first, as a reminder, what is the outcome process? So we are taking a methane source as natural gas or biogas and mixed with oxygen. and this mixture is fed into an OCM reactor, and then is also proposed a post-bed cracking reactor because exothermicity that can be reached on the OCM reactor. Here, a small mark on the OCM reactor, because we are not trying to reach the highest yield possible for the CO2 species or ethylene, but we are aiming the maximum yield and the equimolar mixture of ethane, ethylene, and CO for the further formulation of ethylene in the C123 project. So first, for the lab scale conditions, we use the same operating conditions from which we did the experiments. And the results show that considering the OCM reactor, as the temperature is increasing, of course, we are increasing the yield of ethylene. And the equimolar mixture shown here in green in the right axis of the figure is not reached. I mean, we want to reach this number 1. So because we have ethane and we use a post-bed cracking, the ethane yield is decreased and the ethylene yield increased, showing that the post-bed cracking helps to reach this equimolar ratio and also increase the yield towards ethylene. So now for the real scenarios, we consider natural gas and biogas. So we approximate the composition of these two gases based on literature reference. And first, for natural gas, considering only a temperature of 800 degrees, we could see that considering only those in reactor and the post-bed cracking has a small impact increasing ethylene yield and also the equimolar ratio. But also we could see that the ratio is even higher than 1, which means there is more ethylene than CO. So at 850 degrees, you could see that the methane conversion is increased from 23% to 33%, and the yield is increasing. So this is for the scenario of the natural gas. And for biogas, the ethylene is lower than those seen for natural gas, and the mixture, the ratio between ethylene and CO is lower than the 1% in natural gas. So with this, we can conclude, well, first that the catalyst of manganese sodium tungsten supported on silica is the most suitable, at least for OCOM, because it has the highest ethylene yield. And then based on the experiments done, we saw, we were able to develop this 8-step kinetics model, also following some assumptions because the amount of water we have. And that allowed us to use it on the OCOM simulations. And we could see that the results showed that the maximum ethyl yield is about 50%, which has a molar rate, ethylene to CO ratio of 1.5, which is even higher than the one we wanted for the reformulation of ethylene. Of course, the operating conditions were 850 degrees, total pressure of 1 bar, and the space time of 2.5 kilograms per second. An outlook regarding OCOM is that, okay, in order to improve the kinetic model, more data, more experimental data should be focused on the role of the water. So the effect of water could be captured from experiments. Also, we want to scale up the catalyst to the pellet synthesization in order to test this on their, in a pilot plant industrial scale packet bed. Also incorporating the kinetic model on a reactor model in order to assess what could be the oxidative conversion of methane process performance, and scaling above the process to the pilot plant and the industrial scale. So from my side, that's everything, and thank you very much.
Thank you to you.